Good evening, students. Today we'll discuss about your unit 2, that is the concept is moving loads and influence line diagram. And in the last class, what we have discussed about what is influence line diagram, what is the importance of ILD, and we have also understood how can we construct the influence line diagram or simply supported beam with point loads. And what are the responses uh, of the responses? Like what are the responses in a beam? Let's say your reaction or shear force or bending moment. How can we calculate reaction, shear force, and bending moment by using the help of influence line diagram? So today we'll discuss about same influence line diagram concept for simply supported beam with UDL, right? So how can we construct or how can we calculate? First, how can we construct the ILD for SSB with UDL? And from the influence line diagram, how can we calculate the reactions or shear forces and bending moment? That we'll discuss in details. So when you talk about UDL, so two conditions can be there. So first case will be, case one will be, so what if the UDL is shorter than the span length, span of the beam. This is your case one. Case two would be UDL longer than span. But this was not the conditions when it is point load. As we are testing with the UDL, uniformly distributed load, so these two cases can arise. So you have to see what happens if the UDL is less than span. How can we draw the influence line diagram and we can calculate the shear force and bending moment? If the UDL is longer than the span, how can we calculate the shear force and bending moment? It is very easy. Let us just concentrate on this. So the question says a simply supported beam has a span of 15 meter, a UDL of 40 kilonewton per meter and 5 meter long crosses the simply supported beam girder from left to right. Draw the influence line diagram for the shear force and bending moment at a section 6 meter from left end. So use these diagrams use this influence line diagram to calculate the maximum shear force and bending moment at this point. So here is the case, your beam is 15-meter span length, A, B, and C is the point where we are calculating the maximum shear force and bending moment. And we are considering this UDL 40 kilonewton per meter and the spread length is 5 meter. So as we already know in the previous class that what will be the ILD for shear force at C. So ILD for shear force at C is this with the negative coordinate Z by L and positive coordinate L minus Z by A. Right? If you want to know how to how you have reached at this point, that is Z by L and L minus Z by L, you can refer to the previous class. Okay. So Z by L is here, Z is here. Z is nothing but from the left support to the point where we are calculating maximum shear force or bending moment. So Z distance is 6 meter. So Z is equal to here 6 divided by L is 15. So we got 0.4. The negative coordinate is 0.4 and the positive coordinate is L is here 15 minus Z is 6 divided by 15. So 9 by 15. So it is 0.6. So these are related to got 0.6 and this is 0.4. So we'll see how can we apply this UDL in this influence line diagram and we can calculate the maximum shear force. Coming to maximum shear force, so as it has the negative side and positive side, we'll have a maximum negative shear force and we'll have a maximum positive shear force. So now imagine the UDL is traveling from left to right. This UDL is traveling from left to right. So you just imagine at what position, at what point the UDL will be on the diagram so that we'll get the maximum negative shear force. This diagram is nothing but the influence line diagram for shear force. Means this is the response diagram for the shear force, right? In a unit load. So when we have got the unit load diagram, so we can put any magnitude of load on the diagram and we can multiply with the ordinates. We'll get the corresponding shear force for that particular case. So now see, we have a UDL. So that means you just imagine at what position of the UDL will get the maximum negative shear force. Definitely when one head of the UDL will be on the maximum ordinate, negative ordinate. In that case, we'll get the maximum negative shear force. So if we'll keep this head of the UDL, keep this head of the UDL on the maximum ordinate, where the tail of the UDL will be present, the tail of the UDL will be 5 meter behind the maximum ordinate. So now what we have to do here, the ordinate is negative ordinate is 0.4. So we have to find out what is this ordinate. Let's say y1. What is the ordinate here? 5 meter behind the maximum ordinate, and we can calculate the maximum negative shear force from this. So how to calculate y1? Y1 is from the similar triangle formula we can calculate. What is the similar triangle formula? Let's say here is the bigger triangle, which is 0.4. So another triangle is here, small triangle. Let's say this is y1. So this triangle we can compare and we can write the equation. So it will be, so this is 1 meter from left hand. So 1 divided by 6 meter, 1 divided by 6 meter. So total length is 6 meter. So 1 divided by 6 meter is equal to, you can write like this, 1 divided by 6 meter is equal to y1 divided by 0.4. So from here we can calculate y1 is equal to 1 by 6 into 0.4. So this value 0.0667, we got the value of y1, 0.0667. So once you got this ordinate, so how can we calculate the maximum negative shear force? Maximum negative shear force will be the load into area of the area under the load. Area under the load. So what is the area under the load? The load is spread over this from here to here, 5 meter distance. The load is spread over 5 meter. So the area under the load is, this is the area under the load. So how can we find out the area? This is the magnitude of the load, 40 kilonewton, into area of the area under the load is 0.0667. This is your y1 plus 0.4 divided by 2, okay, into 5. So what, from where it got? So area of the trapezoidum you have to put. Area of the trapezoidum formula I can put. Area of the trapezoidum formula, that is y1 plus the maximum area, that is 0.4 divided by 2 into the height. Height is here 5 meter. So if you calculate this, we are getting now maximum negative shear force is 46.667. I hope you understood this. Now come to maximum positive shear force. So in a similar way, now the load is moving from left to right. So imagine at what position the maximum positive shear force will occur. Obviously, when the tail of the UDL will be on the maximum ordinate, right? So if the tail of the UDL will be on the maximum positive ordinate, Then where will the head? Where will the head? Head will be 5 meter ahead of the tail. So if 5 meter ahead of the tail, so you have to find. We know already the maximum ordinate. What is the maximum ordinate here? Maximum ordinate is 0.6. So we have to find out. Let's say this is y2 value. This is your y2 value. So for this ordinate y2, if you calculate, then after that with a similar formula we can apply like load into area under the load. We can calculate the maximum positive shear force. So how to calculate the y2? The same similar triangle formula I can apply. So y2 is 4 by 9. Why 4 by 9? Look, the total length is here. This length is 6 meter. Total is 15. So this is 9 meter. And what is this length? 9 meter minus 5 meter. Okay, so this 4 meter. Right? So 4 by 9. So similar triangle formula we have applied, the bigger triangle with the smaller triangle. So 4 divided by 9 is equal to y2 divided by 0.6. From this we can calculate y2 is equal to 4 by 9 into 0.6. So we are getting 0.267. So once you got y2, a similar way you can calculate shear force at C, that is load into area under the load, that is 0.6 plus 0.267, that is your y2 divided by 2 multiplied by 5 is nothing but your height. So from here we can calculate 86.67 kilonewton, which is your maximum positive shear force. Right? I hope you understood this. So similar way, how we have calculated maximum negative shear force, similar way we calculate maximum positive shear force. So how to calculate for bending moment? For bending moment, we already know what is the influence line diagram for bending moment at any point. So this is your influence line diagram for bending moment. So what is the formula here? What is the maximum ordinate? Maximum ordinate we already calculated or derived it in the last class. Z into L minus Z by L. So in our case, what is this? So sometimes we call it YC. YC is equal to this. Z into L minus Z by C. So what is the value of Z here? Value of Z is 6 into 15 minus 6 divided by 15. From this we can calculate YC is 3.6. So YC is 3.6. So now the question is, like in previous, while calculating the shear force, what we are imagining and what we are doing, we are keeping one point or one head, either head or tail, on the maximum ordinate, so that we can get maximum negative shear force or maximum positive shear force. But in case of bending moment, you see the distribution of triangle is not symmetric. So from the maximum ordinate to left support is 6 meter and maximum ordinate to right support is 9 meter. So how can we uh, optimize, or how can we position our UDL so that the distribution of the load will be equivalent in the triangle or in the ILD, right? How can you do that? It will be, if you distribute the load, the similar ratio how the triangle is distributed, then only we can distribute, we can parallel the uh, we can distribute the UDL parallel with the ILD, right? So for that, what we can do? So let's say the distance from the maximum ordinate to tail of the UDL is x, and what will be the next? This will be 5 minus x, right? If you write the equation x divided by 5 minus x, because we are going to equally distribute with the triangle. So this, if x divided by 5 minus x means this to this length is equivalent to this length, is equal to, how can equivalent with the triangle, that is 6 divided by 9. So this ordinate to left and ordinate to right length. So from here you can calculate x is equal to 2 meter. So if x is equal to 2 meter, what is the opposite one? 5 minus x, that is 3 meter. Okay, so in a similar way, we have distributed the UDL. So we have positioned the UDL in such a way that we can get the maximum bending moment. We can get the maximum bending moment for the at C, right? So Y1 is, how can we calculate now Y1? What is this Y1 here? So this is the position of UDL. So how to find out the maximum bending moment? The formula will be same. Load into area under the load. Area under the load. The formula will be same. So to find out the area under the load, we need to identify what is this height Y1, let's say, and what is this height Y2. Okay. So first calculate Y1. How to calculate Y1? This is a similar triangle we have to consider. This is the bigger triangle and this is the smaller triangle. So bigger triangle to smaller triangle if we compare. So what would be it? It will be 6 minus 2. 6 minus 2. Why? Because the x is 2. So 6 minus 2 means this length. 6 minus 2 is this length. So this is 4 meter. So 4 meter, 6 minus 2 is nothing but 4 meter divided by 6. So 4 divided by 6. The smaller triangle length divided by bigger triangle length. The ratio is equal to y1 divided by the maximum ordinate, that is a 3.6. Okay. So from here you can calculate y1 is equal to 4 by 6 into 3.6. So we are getting here 2.4. So y1 is 2.4. Similarly, you can calculate y2. Okay. If you calculate y2, this value will be also same. Why this value will be same? Because we have distributed the triangle in similar way. We have equivalented the distribution of triangle as well as the UDL in similar ratio. That's why the height will be y2 will be also same. So the maximum you can, otherwise you can calculate in the right hand side by keeping in or by comparing this larger triangle and the smaller triangle. So maximum moment, how can we calculate now? The load into area of ILD for MC under the loaded length. So the load W is your 40 kilonewton into the area is here one trapezoidal, here another trapezoidal. Trapezoidal 1, trapezoidal 2. Okay. So for trapezoidal 1, what is your area? So 2.4, the y1 is 2.4 plus 3.6 divided by 2 into the height is 2 plus, so here that side also 3.6 plus 2.4 divided by 2 into 3. So from this we can calculate 600 kilonewton meter. I hope you understood how to find out the maximum bending moment if there is a UDL and simply supported beam. Okay. So the second condition, what we have discussed, first what we have understood, that is the UDL is lesser than UDL is shorter than the span. Now let us discuss if UDL is greater than the span. If UDL is greater than the span, so the question, let us read first. The UDL of span 8 meter having intensity 25 kilonewton meter, moving and simply supported beam at span 6 meter. Draw the influence line diagram for shear force bending moment at a distance 2.5 meter from left support. So the UDL length is 8 meter and the span length here is 6 meter. So in that case, the procedure will be same. First, draw the influence line diagram for shear force, where is the negative coordinate is Z by L. Z is here in our case, the distance is 2.5 meter. We are going to calculate the shear force and bending moment at a distance of 2.5 meter from the left. So in that case, here Z is 2.5 divided by L is 6. So we are getting 0.58. In similar way, you find out the positive coordinate, that is L is your 6 area is 6 minus z is 2.5 divided by 6. So we are getting 0.42. Then we'll see how the UDL is moving in the beam and how can we calculate. So the first case is when the UDL is moving from left to right. When the UDL is moving from left to right, so imagine when we'll get maximum negative shear force and what position of the load will get maximum negative shear force. Definitely, like the previous case, the head of the UDL should be on the maximum negative coordinate. Then only we can get maximum negative shear force. So by keeping that, see, and the rest of things will be behind that maximum coordinate. So by keeping that, if you the shear force at C, that is 25 is nothing but your magnitude of the load into area under the load. So area under the load, what is the area here? The area is the whole negative triangle is the total area we have to find out. And this part, which is beyond the area, no need to consider this. Okay. So 25 into 1 by 2, that is half into base is 2.5 into height is 0.42. Okay, so this one, if you calculate, you will get 13.125, the maximum negative shear force, right? So if you go for the maximum positive shear force, same in similar way, the load is moving from left to right. So just imagine when we'll get the maximum positive shear force. The case will be when the tail of the means the total UDL will be on the positive triangle, right? Then only we'll get the maximum positive shear force. So in that case, the tail should be on the maximum coordinate. Tail of the UDL should be on maximum coordinate of the influence line diagram, and it will continue up to B, and the extra part will be beyond B point. So in that case, how to find out the shear force? 25 is nothing but your ordinate, your magnitude of the load into half into base is, what is the base? The base is 6 minus 2.5, 6 minus 2.5, okay, because this part is 2.5, right? So 6 minus 2.5 into the height is 0.58. The height is 0.58. So if you calculate this, you'll get 32.62 maximum positive shear force, right? So in a similar way, I hope you understood this while we are considering the UDL and how to calculate the maximum shear force and bending moment in maximum positive shear force and maximum negative shear force and maximum bending moment. One case also we have missed it here. This is what we have calculated. That is shear force. For bending moment also, what we can do for bending moment, what was the ILD? ILD is, let's say, this is the ILD, right? This is the ILD. Okay, the maximum coordinate, how to find out? Z into L minus Z by L. So we'll see how much it is coming. How much it is coming, you can see. Okay, Z is here. Just calculate. Z is here 2.5 into 6 minus 2.5, that is 3.5. 2.5 into 3.5 divided by 6. Okay, so if you calculate this value, we can get 2.5 multiplied with 3.5 divided by 6. This is 1.458. So 1.458. So 1.458, let's say 46. 1.46. So on the ILD for bending moment diagram, this is 1.46, and we'll place the UDL. Over the entire ILD for bending moment. right, over the entire triangle. That is 25 kilonewton per meter. So you see what is the ordinate? No need to find out the ordinate. Directly you can calculate load, maximum bending moment, maximum bending moment, maximum bending moment is load into area under the load, right? So what is the load? 25 kilonewton into area under the load is half into base is your 6 meter into height is your 1.46. Just calculate whatever value you will get, that will be the maximum bending moment, right? So yeah, next we'll see a different questions where in case of the simply supported beam, if both types of load is present, our point load is there as well as UDL is there, several point load is there in different locations. So in that case, how can we find out the maximum shear force and maximum bending moment at a particular section, right? So here, let's say it is telling to find out the question it is saying find out the maximum shear force and bending moment at a point C here, which is 4 meter distance from the left support, right? As we know, the first step what we can do, first step is draw the influence line diagram for shear force. So influence line diagram for shear force, we already know there will be a negative coordinates and positive coordinates like this. Okay. So what is this? What is this value? This value is Z by L. So Z is 4 meter. So Z is 4 meter divided by L is 14 meter. So if you simplify this, it will be 2 by 7. So this is 2 by 7. Okay. And what is this value? L minus Z by L. Okay. This is 5 by 7. Right. So now we'll find out all the ordinates under the load. So what different thing we'll do here? So you see the diagram, how many loads are there. So first of all, one load is there 40 kilonewton, another load is there 60 kilonewton, another load is there point load that is 80 kilonewton, and UDL is there 10 kilonewton per meter. So we'll identify what are the ordinates under the loads. So now quickly we should calculate now. Initially we are taking time. So now if the ordinate is 2 by 7, maximum negative ordinate, what will be the ordinate? That is 2 meter distance, 2 meter from that. So use the similar triangle formula, and from the similar triangle formula you can apply with 2 meter, and this is also 2 meter. So 2 divided by 4, 2 divided by 4 is equal to y1 divided by 2 by 7. So from here, what can you calculate? 2 into 2 by 7 is equal to y1 into 4. So from this we can calculate y1 is equal to 2 by 4 into 2 by 7. So 1 by 2, 1 by 2, so 2 by, so 2 cancels, 2 cancels, so 1 by 7. So y1 is 1 by 7. Similar way, we can find out the ordinates of the positive side. So here the maximum ordinate is 5.5 by 7. So use this similar triangle, this bigger triangle and the smaller triangle, and we can find out what is the ordinate here. Why you are calculating the ordinate here? Here means what is the distance? Distance is 2 meter from the maximum ordinate. Why we are calculating? Because this point, this UDL head of the UDL is situated 2 meter from point C. Okay. So then after 2 meter, calculate this ordinate. Then after 2 meter, calculate this ordinate. Right. So use the similar triangle formula. So once you calculated the ordinates, it will be easy for us to calculate the shear force at point C. Why? When what is the formula? Formula is load into area under the load, or the ordinate under the load. If it is a UDL, so area under the load. If it is a point load, then ordinate under the load we have to consider. So here you see Here you can see the load is 40 kilonewton. First point load is 40 kilonewton. So 40 kilonewton into what is the ordinate? 1 by 7. The y1, the ordinate is 1 by 7. This is nothing but your ordinate under the load, right? 1 by 7 minus 10 nothing but your UDL, 10 into, in case of UDL, what do we have to do? Area under the UDL. So 10 into half into 1 by 7 plus 2 by 7 area under the trapezoidum. Basically, we are calculating area of this trapezoidum. This trapezoidum area is 1 by 7 plus 2 by 7 divided by 2 into distance is 2. This is what we have written, 1 by 2 into 1 by 7 plus 2 by 7 into 2. This is the area under the UDL plus 10. This is the half of the area. Another half we have the positive side, we have to find out. Positive side is then 10 into half into 5 by 7 plus 4 by 7 into 2. I have understood this calculation, right? Plus 60. 60 is nothing but your second point load. 60 into what is the ordinate? 3 by 7. 3 by 7. 60 into 3 by 7 plus 80. 80 is nothing but your third point load. 80 into 2 by 7. 2 by 7 is ordinate under the point load. So if you simplify this equation, we are calculating 51.43 kilonewton, that is shear force at C. Right? So next we'll go to how to calculate the bending moment. So how to calculate the bending? Yeah. Next we'll see how to calculate the bending moment. So what we did, we know already what is the ILD for bending moment. So this is the triangle we have to find out. We have to find out what is the height here, YC. So YC is, we know the formula, Z into L minus Z by L. Or I have written here X into L minus X by L. So by using this formula, so put the value of Z is equal to 4 meter and L is 14 meter. So you can get 20 by 7. So YC is 20 by 7. So previously we have calculated, now we'll calculate for Y1. So how to calculate Y1? Y1 is nothing but this first ordinate under the first point load. So that is the Y1. How to calculate? Use the similar triangle formula. Let's say this is Y1. This is what we have calculated, 20 by 7. So this smaller triangle, let's say this distance is 4 sorry, out of 4 meter is 2 meter and total is 4 meter, right? So how can you calculate? So y1 divided by 2, so y1 divided by 2 is equal to your 20 by 7 divided by 4. That is what we have written here. So from this we can find out y1, that is 10 by 7. Similar way we can calculate y2, y3 and y4. So y2 is 16 by 7, y3 is 12 by 7 and y4 is 8 by 7. So once you got these ordinates, we can find out the maximum bending moment at C. That is load into, what is the formula? Load into ordinate. If it is the point load, if it is the UDL, it will be load into area under the load. Okay, so MC is equal to, we can calculate 40 into 10 by 7, that is your Y1, plus 10 into half into your area of this trapezoidum, 2 trapezoidum area we have written here, into 2 is the height, then plus 60 into, this is your second point load, 60 into 12 by 7. 12 by 7 is nothing but your Y3 plus 80, that is your third point load. 80 into 8 by 7 is your Y4. So if you calculate this, you will get 345.71 kilonewton meter. That is the maximum bending moment under point C. So this is a question. You can solve at your home. You can practice it. The summary of the lecture, you can go through what is the importance of IDL, how can we ILD, and how can we find out the responses. Okay, responses means your shear force and bending moment. Shear force and bending moment by using the ILD if there is a UDL as well as point load. So these are the today's discussion. I hope you understood this. If you have any questions, you can ask. Otherwise, we'll wind up this session. Thank you very much. We'll see in the next class.